Welcome back, and in this lecture, we are going to learn about closures of relations. So, we already have seen different types of relation like reflexive relation, symmetric relation, transitive relations, and their opposite, right? Like irreflexive, asymmetric, antisymmetric, and all. So, in this lecture, we are going to learn about the closures of relation. So, the very first relation we learned about is a reflexive relation. So, here we are going to learn about the reflexive closures on R. Okay. So here reflexive closure means the smallest possible reflexive relation containing R. Okay. We'll see what does that means. But first understand reflexive relation, the smallest reflexive relation containing R is known as reflexive closure on R, or is known as reflexive closure of R. Okay, so if R is a relation, we have to construct a smallest reflexive relation that will be containing R. So, for example, let's say we have R and the relation R is like containing 1 1, 2 2, and 2 3. And this is a relation defined on set A, and A contains elements 1, 2, and 3. Now, let's say we have to construct the reflexive closure on R. So, it is denoted by RR, and the smallest reflexive closure. So this relation is definitely not reflexive because 1 1 is present, 2 2 is present, but 3 3 is not present. So, we have to construct a relation that will be containing R, but it is also reflexive. The only thing missing in this relation is 3 3, right? So what we will do, we will add it here: 2 2, 2 3, and then 3 3. Now this is a reflexive relation because for all A present in set A, we have AA present in R. So this is reflexive, and this is the smallest possible reflexive relation containing R. So we can say that there are two results. First is R is reflexive. R is reflexive if R relation R is equal to its reflexive closure. First thing. And if it is not reflexive, though, how to make it reflexive? So RR is equal to R union and delta. So delta will be containing 1 1, 2 2, 3 3, like that. So reflexive closure is R union delta. So keep this in mind. So this is about reflexive closure. Next is symmetric closure. Okay. So let's see what is the symmetric closure. So second is symmetric closure of R. Symmetric closure of relation R. So it is denoted by RS, and RS is the smallest symmetric relation containing R. RS is the smallest symmetric relation containing R. Okay, so now this we can see with the help of an example. So let's say we have a relation R, and R is equal to, let's say, 1 2, 2 1, and 2 3, and this R is defined on a set A, and a set A consists of 1 2 3, all these elements, right? Now if we need to find the reflexive closure of R, then we need to see that if 1 2 is present, 2 1 needs to be present, but if 2 3 is present, 3 2 needs to be present. So we will construct it like 1 2, so 2 1 is there, 2 3, then 3 2 must be there, right? So this way RS is the smallest symmetric relation, it is a symmetric relation that contains R, right? So it is called the symmetric closure. So we can have two results like before. Is first one is R is symmetric, R is symmetric if and only if R is equal to RS. So R is symmetric if R is equal to RS. And the second point is that to obtain RS, so RS, how we can obtain RS? So we can obtain RS by, if 2 1 is present, then its inverse would be 1 2. Okay, so RS equal to R union R inverse. Okay, so this way we can obtain the symmetric closure. So this is very important. To obtain reflexive closure, we are doing union with delta, and here to obtain the symmetric closure, we are doing union with inverse, because we already have learnt about one relation, inverse relation earlier also. I mean, in the very first we learnt about inverse relation. So what is an inverse relation? Just making a note here. So basically, inverse relation is something like if R is a relation defined on a set A and B, then R is a subset of A and B. So R inverse will be defined on B cross A. So such that R inverse equal to AB, right? Such that BA belongs to R. So we are just inversing the order. So order is inversed here. Okay. That is why for constructing the symmetric relation, so if R is a relation which is not symmetric, so R contains elements A, B. So to construct it into a symmetric relation, we need to have R inverse and we need to take their union, so that the new relation RS, smallest symmetric relation containing R, should be covering AB and then BA, right? So RS should be equal to R union R inverse, right? From here we will get. So this is the smallest symmetric relation defined on R. Okay. There are further results like we can note from take a note from here, like if R is a relation, R be a relation defined on A. Okay, so R square equal to RR, RQ equal to R square into R, and Rn plus 1 equal to Rn dot R. Okay, this is very important. Now let's learn about the third type of closure, that is called the transitive closure. So the third type is transitive closure on R. Okay, so this is transitive closure on relation R, and it is denoted by R plus. Okay, that was RF. This is RS, and of course, transitive closure is, sorry, reflexive was RR, and RS, and this is R plus. Okay, so what is the transitive closure on R? Smallest relation, smallest transitive relation containing relation R. Smallest transitive relation containing relation R. Containing relation R. Now, this is a little bit trickier to find the transitive closure, as we discussed earlier also. So let's discuss the results. So if so R is transitive, R is said to be transitive if R equal to RT. That is R equal to its transitive closure. And let's say if we have cardinality of set A, then the transitive closure on A will be defined as R union R squared union RQ union, so on up to Rn. So we are taking the union of all the this. So this appears something a little bit trickier. So just for the time, just keep this in mind, and we'll see how this is calculated. So to calculate the reflexive closure on set A, which contains n elements, so this is the cardinality of set A. Let's say the cardinality of set A is n, and if we are defining a reflexive closure on A, so it will be the union of R union R to the power 1. Okay, sorry, this is 1, this is 2, this is 3, so on up to union up to R to the power n. So this is very important, and this we will be calculating with the help of Warshall's algorithm. Okay, so we'll see next is called Warshall's algorithm. Okay, Warshall's algorithm, right? So this is what we will be studying in programming part also. It's time complexity is given as order of n cube, so it is a little bit complex, but here we'll see in simple terms. Let's with the help of an example. So let's say we have a set A, 1, 2, 3, 4. Now you see the cardinality of set is 4. So if we calculate, we have to calculate the reflexive transitive closure on A, then it will be R union R squared union RQ union R4, right? So this will be, now how we will be calculating it. So first we will define a relation R on set A. So relation R is, let's say it's 1 comma 2, then it's 2 comma 1, then 3 comma 4, and 4 comma 3. It is obviously not transitive. Okay, and this algorithm is also used to check the transitivity, whether it is transitive or not. And how to check? If R is equal to R closure, then R is transitive, right? So closure is used to check whether it is transitive or not. So we will be checking this with the help of Warshall's algorithm. For that, we will first draw the matrix representation for R. So here, what we will do, 1 2 3 4, and 1 2 3 4, and here for 1 2 it's 1, and remaining it is 0. Then again 2 1 is 1, and remaining it is 0. 3 4 is 1, and remaining it is 0. And 4 3 is 1, and remaining it is 0. Okay, so this is R0. Okay, now we will convert it into R1 R2 and 3. So what we will do here to construct MR1. Okay, so MR1 will be something. So what we will see, so we will take the first row and first column. So I'm just taking another pen. So we will take the first column, and we will take the first row. We will exclude that, and in the remaining, what we will do, we will do like this one, and this one, and then this one, and this one. So we will ignore these two. And whatever is remaining, so this 0 is remaining, we will convert it to 1. Okay, so basically what we are doing, we are converting the uncrossed 0 to 1. Okay, so this we have excluded, and for the remaining we are just crossing it this way, and whatever it is uncrossed we are converting into 1. So that's how we will be obtaining the MR1. So that is equal to 0 1 0 0 1 1 0 0, and 0 0 0 1, and let 0 0 1 0, right? So this is MR1. Now in the next step for obtaining MR2, here what we will be doing, so again we will take the second column, okay, and the second row. So we will exclude it, and for the remaining, what we will do, again we will take it into this way. So we will take like this. Okay, Oh, sorry, we don't need to, we don't have to touch this part, right? So we will take whatever which is untouched here. So again we will do like this. Just a second. Okay, let me do it with the same pen. So we will take this part, this one we will exclude, this one we will exclude, this one we will exclude, and this one we will exclude. So the untouched is this 0. So what we will do, we will convert it to 1. Okay, so we obtain the mr2 part, and that is equal to 1 1 0 0 1 1 0 0 0 0 0 1 and 0 0 1 0, right? Now in mr2 step, again what we will do, let me change the pen. Okay, so here we will take the third row, this third row, okay, and the third column we will exclude. Now, after excluding this third row and third column, again we will take the row like this. So what here we are doing, just take this row, then this row, and this row. Okay, so this comes here. Now all these are taken. What is remaining? This 0 is remaining. So this is untouched. We will convert it to 1. So now it becomes mr3 is equal to 1 1 0 0 1 1 0 0 0 0 0 1 and 0 0 1 1. Okay, so this is mr3. Now in we have to obtain mr4. So for obtaining mr4, again what we will doing, uh, we will be taking the fourth row. This fourth row will exclude, and fourth column we are excluding, right? So now from where we have to cut this. So whatever is coming as like, here we have something called this part. So we will take this one out, this one out, and then what we will do, we'll take this one out and this one out, right? So these we are taking out, and whatever is untouched here, right, that we will convert to 1. Okay, so basically to strike out this part is important. So I we are first taking out the fourth row and fourth column, and then whatever we are doing, we are just striking out this part altogether. Okay, and whatever is the untouched 0, we are converting into 1. I'll show you again this process, but let's say what is being obtained at mr4 is 1 1 1 1 0 0 0 0 0 0 0 0 1 1 1 1. So if it is 1 2 3 4, 1 2 3 4, so in mr4 finally we have obtained the transitive closure, and that is equal to 1 1 1 2, okay, 2 1 2 2, and then 3 3 3 3 4, then 4 3, and then 4 4. So this is the transitive closure on relation R. So basically what we are striking out is important here. So in every step we strike out only those column and those rows that contain 1. Okay, so there are two things you need to note in this case. Let's see it with another example, although I have kept that example for digraph method. But let's see this with the help of another let's see with yeah, another example. Let's see, because that way it will be more easier to understand. So the same Vossel method, but with different example. So here also we have relation A given as set A given as 1 2 3 4, and we are defining a relation on set A, and that consists of 1 2 2, 3, 3, 4, and 5, 4. Okay. So these are some elements of the relation R, which is defined on set A. Okay. Now, to construct the Warshall method, what we'll do? We'll consider first MR0. So in MR0, we'll draw the initial state. So 1, 2, 3, 4. Okay. And 1, 2, 3, 4. Right. So for 1, 2 will be 1, remaining 0, 0. For 2, 3, it will be 1 and remaining 0, 0. For 3, 4, it will be 1. And for where is this 5 coming? I think it should be. Where is this 5 coming? So I think it is. It does contains 5 also, right? I didn't notice. So this is the relation. So we have one more entry, 5. Let's include this. Okay. So let's include this. So we will be doing this 5 times. Okay. So this will get enlarged with the number increasing. That is why the complexity is huge. So do we have 4 entry? No. So let's just strike it down. It will be all 0. Okay. Since there is no connection for 51000, there is an entry called 54. So it is 1 and it is 0. So this way we are constructing MR0. Now, in first step, what we will do? So here we are taking the first row, okay, and the first column, right? Bear with me, it will take some time longer. So we are taking first row, first column, and then wherever there is a 1, okay, we are striking out that part. So here is 1, here is 1, here is 1. So what we will do? The column and the row we need to strike out. Okay. So how we are going to do this? We will be striking out like this and this. Okay, so this is strikeout. It's again very much confusing. Let's strike out in a uniform way. Okay, so we are striking out this entire part, and we are striking out this part. Okay, so we just striked out column, this column, and this row. Okay, then we striked out this row and this column. Okay, then we striked out this row and this column. Now wherever there is 0, we will be changing it to 1. Okay, so untouched 0. Okay, so this is untouched 0, it is 1. Here is this untouched 0, is it? No, it is not untouched 0. See, we striked out this, we striked out this. Okay, so I think this is the untouched 0, so we will be converting it to 1. Okay, so beware while you are striking out the rows and columns. Okay, now we obtain something which is 0, 0, 0, 0, 0, and 1, 0, 0, 1, and 0. Okay, and then we have a 0, 1, 0, 0, 0, and then we have 0, 0, 1, 0, 1, and then 0, 0, 0, and 1 and 0. Okay, now we have mr, uh, we will be constructing mr2 from this. So let me do the striking up from different color. Okay, let's choose black. So this, in this case, we will strike out the second row and second column. and wherever it is 1 here. Okay, so where it is 1, so this column it is 1, and this row we need to strike out. Okay, and again it is also 1 here, so we will strike out this one and this one, and there is 1 here also, so we will strike out this one and this one. Okay, so here it is 0, so we'll make it 1, and here also we'll make it 1. Okay, so what we obtained, 1 0 0 0 0, and then 1 0 0 1 0. It was 1, right? Okay, and then we obtained 1 1 0 0 0, then 0 0 1 0 1, and then 0 0 0 1 0. Okay, this we obtained. Now this is our MR2. Okay, now we will cut the third row and third column. Okay, so third row and third column, and then wherever there is 1 we will strike out, so we strike out this part. Okay, for this one we striked out this, for this one we striked out this and this. Okay, then for this one we striked out this and this, right? That is why I need to use different colors. Okay, so these are covered. Now for this one we striked out this and this, so it is already striked out. Okay, and now for this one we have striked out this and this. Okay, and for this one also we will strike out this and this, and for this one also we will strike out this and this. So I think it will remain the same for MR2. So MR3 will be constructed from here. So it will contain 1 0 0 0 0, then 1 0 0 1 0. See how complex it is getting. 1 1 0 0 0, and then 0 0 1 0 1, and then 0 0 0 1 0. Okay, and in this case we will, let's change the color for that. So here we are striking out fourth row and fourth column, and wherever there is one, so wherever there is one, so obviously this row and this column, for this also this one and this, and for this also this one and this, and for this one and this, for this this one and this. Now what's remaining, I believe this already we have crossed, so this row is remaining, so we'll convert it to 1, and this one also we are converting to 1. Now let's say what we get in MR4. So MR4, I'm not sure whether we'll get correct, but let's see, because in one we haven't reduced it, right? So let's see. Then 1 0 0 1 0, then 1 1 0 0 0, then 0 0 1 0 1, and then 0 0 1 1 1. Okay. Now what we will do? Okay, now we have to calculate MR5, and let's do it with green. We will cut this row and this row, and wherever there is 1 here, so obviously this and this and this and this, for all these three. And for second one, this one and this one. For this third one, this one and this one, and also one. for this one, and this one, and for this one, and this one. So all reduced. So I think our final one will be looking like this, like 1 0 0 0 0 1 0 0 1 0 1 1 0 0 0 0 0 1 0 1 and 0 0 1 1 1. Okay, so it is 1 2 3 4 5 and 1 2 3 4 5. So if we construct the R transitive closure from here, so it will contain elements like 1 1, okay, 1 2, 1 3, right, and then 2 3, okay, 2 3, then 3 4, right, and 3 5, 3 4 and 3 5, then 4 2, okay, and 5 4 and 5 5, okay. So first we'll check whether our original relation is there in this. So our original relation contained the elements 1 2, 2 3, and 3 4 and 5 4. Apart from that, we have entries like this. So let me match. So it is 1 1 1 2 2 3 1 3 3 4. I don't think we have the correct match for that because somehow we messed up in some way. So it is not the right closure because here only if you see 2 3 is present, 3 4 is present, and we are searching for 2 4 which is not present. So this is not the right closure. So whatever we did was a waste of time. So that's why manually we don't prefer this way, doing this way. So hence we have adopted another method called the diagraph method. Okay, so we have this diagraph method. That's why I wanted to introduce this, because it is very tedious to do Warshall's way, right? So this is the easiest way to calculate the transitive closure. So let's say we have A, and we'll see with the previous example how easy it is. So A consists of 1 2 3 4, and there is a relation R on it, which consists of 1 2 2 1 3 4 and 4 3. Okay, now we have to construct the closure on transitive closure on R. So what we will do, for 1 2 and 2 1, we will make like this 1 2. So from 1 to 2 and from 2 to 1 there is this arrow. So on an extra we will include this from 2 to 2 and 1 to 1. Okay, again we have 3 4 and 4 3. Okay, so for 3 4 and 4 3 also we'll do the same thing. So 3 4 and 4 3, so 3 to 4 and 4 to 3. Now here we will construct an extra line, so like this. Okay, why we are doing this? Because from 1 to 2 there is a way. Okay, so we will construct whatever is missing. So from 1 to 2 and 2 to 1, this is a cycle. So we will construct from 1 to 1 and 1 to 2, so that it should come back like this, like there should be cycle onto this. Okay, so all together if we join, then transitive closure will be 1 1, okay, 1 2, then 2 1, right, and 2 2. Again for 3 4 it will be 3 4, 4 3, and 3 3, and 4 4. So this is the transitive closure on R, right? It will be clearer with the next example why we did this. So let's say we have a relation R defined on the same relation. uh, let's say the set is 1 2 3 4 5. Okay, so number of elements have increased. What happened? Yep. So here, if we are defining the relation R on this set, and the relation include 1, 2, then comma, 2, 3, then comma, 3, 4, and then 5, 4, right? So for each, we will draw the digraph, like we'll take it as the nodes 1, 2, 3, 4, and 5. And from 1 to 2, there is an arrow. From 2 to 3, there is an arrow. From 3 to 4, there is an arrow. Okay, and from 5 to 4, there is an arrow, like this. So it is from 1 to 2 and 2 to 3. So from 1 to 3, we will draw so like this. That's just this. So from 1 to 3, we will be drawing an arrow like this. Okay, so because from 1 to 2 there is an arrow, 2 to 3 there is an arrow. So from 1 to 3 we'll draw an arrow like this, right? Similarly, uh, it is for 2 to 3 there is an arrow, and 3 to 4 there is an arrow. So we will draw an arrow from 2 to 4. Okay. Similarly, if we see from 1 to 3 there is an arrow, 3 to 4 there is an arrow. So 1 to 4 there will be an arrow. Okay. So this way we will construct for each one like this. So first we will take 1 to 2. So 1 to 2 there is an arrow. 2 to whatever there is an arrow. So we will do this way. Okay, 2 to 3 there is an arrow. Now 3 to 4 there is an arrow. So we will make this from 1 to 4 like this. Okay, so this way we will construct no more arrows are required for 5 to 4, because from 4 there is no outgoing arrow. So from here we will get the transitive closure on R as 1 comma 2, 2 comma 3, 3 comma 4, 5 comma 4, and also 1 comma 3, and then 2 comma 4, and then 1 comma 4. Okay, so this is the transitive closure on R. So this way, using the diagraph method, it becomes easier. So yeah, we can use the diagraph method for calculating the transitive closure. So that's it for this part. And if you do have any comments or question, please do post in the comment section, and I'll close this part here. And yes, thank you very much.